So, all right, let's begin the lecture. So, this is an introductory, this is a course on Galois Theory. So, we assume that you are familiar with ring theory. And, so, familiar with ring theory. So, and you know what an integral domain is, what a field is, what a unique factorization domain is, what Euclidean domain is, what a PID is, and so on and so forth. And, so if R is an Euclidean domain, this is the main theorem which we will be using in the sequel. So if R is an integral domain and Fp it's a field of fractions, and if you pick a polynomial f of x in R bracket x, so f is irreducible. R is a UFD, not just an integral domain. R is a UFD. F is irreducible over R if and only if f is a primitive and f is irreducible over f. Okay. So let us. So this is the main theorem which we are going to use in this the next few lectures. So with this, let us try to so just give me a second. So correct. Okay, so one of the main topics of the Galois theory is to find steady polynomial equations. Hello. Steady polynomial equations. So so this is how it all started. That Z be the ring of integers, and consider the equation 2x plus 3, and it is clear that this equation has no solutions in Z. So in order to find solutions, that is to say, there is no element in Z for which 2x plus 3 is equal to 0. Okay. Because 2x is equal to minus 3, and you can easily see that minus 3 is a prime number and it cannot be factored into 2 times some number. So in order to find solutions for this equation, you need to move on to the field of rational numbers, where you will have x is equal to -3/2 as a solution for this equation. Okay. So in the same fashion, if you try to consider this equation, x squared minus 2x minus 1 is equal to 0 over q. So you see, by completing the square, x squared minus 2x plus 1 minus 2 is equal to 0. So this is x minus 1 whole square minus 2 is equal to 0. So this implies x minus 1 is equal to square root of 2 plus or minus, and x equal to 1 plus or minus square root of 2. Okay. So you see from this that so you already know that the square root of 2 does not belongs to q, and it is a real number. And from this you see that this equation has no solutions over q, but this has solutions over r, the field of real numbers. Okay, the field of real numbers. Or else you may, so but you can see easily that q is a countable field and r is uncountable from Cantor's theorem. And you want to see whether there is any subfield, some subfield which is economical, in the sense that in the following sense. So if you consider the field, the ring, the field consisting of numbers r plus s square root 2, where r and s belongs to q. This can be easily checked to be a field because the product of two elements. So it is obviously a ring, and any non-zero element has an inverse 1 over r plus square root of 2, which is the form r minus square root of 2 over r square plus 2s square, which is r over r square plus 2s square minus s over r square plus 2s square, square root of 2. So this is an element of q, and this is an element of q. Therefore this, so every invertible element, so every non-zero element in F is invertible, and therefore F is a field. And over this field, since root 2 belongs to F, and of course 1 belongs to F, and therefore plus square root of 2 minus square root of 2 belongs to F, and 1 plus square root of 2 and 1 minus square root of 2 belongs to F. And you can easily see, so that implies that over this field F, this equation has roots. And so F is clearly a countable field, and while R is uncountable. And the main goal of Galois theory is to describe these kinds of fields. What is the smallest field over which a given polynomial splits, whatever that polynomial is? And you want to know, you want to study such kind of field extensions. Okay, so the main goal. So given let K be a field and F be a polynomial over K, that means it has coefficients over K. And the goal is to find a larger field L such that F considered as an element of containing K, such that F considered as an element of L bracket X splits as a product of, splits into linear factors. And if possible, find them. Can you do it in an economical way? So that is the question. Okay. So this is the motivation for studying polynomial equations and how for the Galois theory. And you will see many uses of polynomial equations and their study by means of Galois theory. So let us start the theory. with the following definition. So what is a field extension? Okay. So the definition is as follows. A field extension is a triple IKL where K sits inside L as a subfield. So I of K. So the inclusion map I of K is usually this inclusion is usually denoted by this tower. So a field extension is a triple IKL where K is the domain for I and L is the range for I and K sits inside L. And of course, you know that kernel of I must be trivial because any ring homomorphism I maps 1 to 1 and therefore one cannot belong to the kernel of I, and therefore since K is a field, the only non-trivial ideals are either the trivial ideal and the complete ideal K. And therefore I must be injective. Any ring homomorphism between two fields must be injective. So supposing the assumption that 1 maps to 1 and 0 maps to 0. So that is part of the definition of a ring homomorphism. Okay, so this is called a field extension, but we don't make this, but we tend to abuse the notation and simply say that L over K is a field extension. Because anyway, you can, by means of I, you can identify I with I of K. And instead of distinguishing I as I of K over L, we simply write L over K. So this is the notation. But this triple notation is useful when you try to prove that there exists an algebraic closure for any field. So I guess that's the only case where you need to use this precise definition. And the rest of the times you can get away with this sloppy notation, L over K. And that is what we are going to assume in the rest of the course. So for example, when you say C over R is a field extension, what you really mean is R is sitting inside Q, where a real number is sent to R plus I times 0. So here this is my I, and I of R is R plus I times 0, which you usually denote it as R. But if you remember, C is the set of all tuples A comma B, where A and B belongs to R, such that A1 plus A1 comma B1, A2 comma B2 is equal to A1 plus A2 comma B1 plus B2, and A comma B times C comma D is equal to AC plus BD, AC minus BD comma AD plus BC. So this is the multiplication. So with this addition and with this multiplication, we can easily check that this set is a field called the field of complex numbers, and R sits inside C as R comma 0. But instead of distinguishing it this way, we usually simply write it as R. This is simply denoted by R. Okay, so this is abuse of notation, but a convenient one. So this is the definition of field extension. A field extension is a triple consisting of two fields K and L, and a map from K to L, a ring homomorphism from K to L. And the next one is, so we want to measure. So let us see we want to see the difference between these two extensions. So we had, I already told you that this one is a much bigger extension much larger extension compared to this one. Okay. And therefore we want to actually, so what do I mean by big? And what do I mean by small? mathematically. So I want to quantify this. So the way to quantify is we want to measure how big an extension is, and the way to do that is to consider the extension L over K as a vector space over K. And once you consider L as a vector space over K, you can talk about the dimension of the vector space L over the base field K. And you say if the dimension of if L1 and L2, and if there are two fields like this, and if the dimension of L1 over K is less than dimension of L2 over K, you say that this extension is smaller compared to this. Okay. So, but this is not a very precise notion in the, so you cannot easily see, because what happens if both these extensions are of the same degree? Well, so this notion does not distinguish such cases. So this notion is very coarse notion. So, but this notion actually distinguishes these two cases, because R considered as a vector space over Q is infinite dimensional, while Q of square root of 2 considered as a vector space over Q is finite dimensional with basis of dimension 2, basis 1 comma square root 2, one basis. Okay. So recall what a vector space is. You already know that L is a field, and therefore you have a multiplication map, and you have an addition map. This is my addition map, and this is my multiplication map. So you restrict this multiplication map to K. Okay. So so this is called scalar multiplication. So this is a scalar multiplication is simply the restriction of dot to this. So L together with these two maps can be considered as a vector space over K. Okay. And the degree of the extension L over K is denoted by this, like this, is the dimension of the vector space L over the base field K. Okay. So in this you say that the degree of R over Q is equal to infinity, and the degree of Q of square root of 2 over Q is 2. Okay. And the first theorem of this course is the following theorem. Let M over L and L over K are extensions. Then the degree of M over K. So you can consider that M is an extension over K. Then the degree of M over K is the degree of M over L times the degree of L over K. Okay, this is the first theorem. So in other words, the degree of an extension is multiplicative. Right. So the main aim of this course is to study. So given a field K and an extension, you want to study this extension. So for example, you want to ask questions like what are all the subfields of this L over K? Subfields of L over K. Okay. So in order to study all those things, the first notion we have is the degree, and this degree behaves quite nicely. The proof. So suppose both the degrees are finite. Okay, that means to say that M considered as a vector space over L is finite dimensional, and similarly the vector space L over K. So let x1 up to xn is a basis of M over N. That is, every element can be written as a unique combination of unique linear combination of elements x1 up to xn. Now, similarly, L is let us say it is the degree is m, and it is a vector space over K is equal to K by 1, K by 2, and so on, K by n. Now, if you take an element, let us say, so that these match with M and L. So let us say alpha is an element of M. Then the thing is, the alpha can be written as alpha 1 x1 plus alpha 2 x2 plus alpha m xm for unique alpha 1, alpha 2 up to alpha n. Or better, for a different notation, let's take this. So alpha is equal to L1 x1 L2 x2 plus Lm xn. Now these L1, L2 up to Lm are unique, belongs to L. So this is the crucial part. So they are unique for a given alpha. So that follows from the definition of the basis. Now each alpha Li, each Li belongs to capital L, and it is also a linear combination of y1, y2, yl with coefficients in K, and these coefficients are uniquely determined. So alpha ij, no, Kij, Ki1, y1, Ki2, y2, plus Kil, Yel. So if you substitute this for each I is equal to 1 up to m. For 1 up to m, sorry. Because we are doing it for these coefficients. If you substitute this in alpha, what you will get is alpha can be written as a linear combination of Kij, Xi, Yj, where these Kij are unique. Okay. From this, it follows that by the recall what a basis is. Any set of elements is a basis if and only if each and every element, every vector can be written as a unique linear combination of the basis elements, of those basis elements. And therefore, you can easily see that from that equivalence, it follows that Xi, Yj, where I varies from 1 to m and j varies from 1 to l, is a basis of m over n, m over k. So from this, it follows that m over k is finite dimensional, and since any basis of m over any basis of a vector space has the same number of elements, it follows that m over k is equal to the number of elements of Xi, Yj, which is m times n, which is precisely what we need to show. Equality. Okay, so from this, if these two are finite, then this is also finite. So if we had proven this thing, if m over l and L over K are finite, then M over K is also finite. Conversely, if M over K is finite, we want to show that each of these are also finite. So M is a vector space over K, okay, and M can also be considered as a vector space over L because L contains K. So what I mean by that is, if you have multiplication in M, you can either restrict this multiplication map to K to get this map. So this gives a vector space structure of M over K, or you can restrict this multiplication map to L and get a vector space structure over M over L. Now, since M over K is suppose we are showing the other thing. If M over K is finite, then we want to show that M over L is also finite and L over K is also finite. All right. So if M over K is finite, that means each and every element of M. So there exists, let us say this is M number of elements. Each and every element of M, of capital M, can be written as a unique linear combination of, let us say these are x1 up to xm, okay, z1 up to zm, k1 z1 up to km zm. So this k1 up to km are unique. But if these ki are also considered as elements of L, this does not change. You see? So this implies the dimension of M over L is at most M, because each and every element of alpha can be written as a linear combination of these. Note that these elements Z1 up to Zm need not be linear independent if you consider them over L. So there may possibly some linear combination, some non-trivial linear combination if you consider Z1 up to Zm with coefficients in L. But I don't need that. All I need is, so if you have a spanning set, you already know that the basis is contained in the spanning set. So I know that Z1 up to Zm is a spanning set of M over L. That means the basis, the number of elements in the basis elements, which is the degree of M over L, is at most the number of elements in the spanning set Z1 up to Zm. That is, which is equal to M. So since the dimension, so we can see from this that this is also finite because it is bounded above by M. Finally, we want to show that L over K is also finite. Now, each and every element of L can be considered but the problem is you won't have okay, so L is a subspace of M over K. So you have learned in linear algebra that if V is a vector space and W is a subspace of this, both of this over the same field, then the dimension of W is less than or equal to dimension of V. So you can consider L as a subspace of M over K. From this it follows the dimension of L over K is at most the dimension of M over K. But the dimension of M over K is M, the degree of the extension, and the dimension of L over K is degree of extension. So from this it follows that this is also true. So why do we need to take so much pain to prove this thing? From this, M over K is equal to M over L times L over K. So it follows that if at least one of these extensions is finite, if at least one of these extensions is infinite, the other one is also infinite. So if this is infinite, then one of them must be infinite. If one of them is infinite, this is also infinite. Or if both are finite, this is also finite. Okay. So that is the main thing. So, so we will be considering a tower of extensions, which is of the form kn minus 1, kn minus 2, and so on, k1, k0. And you can see that the degree of this, so by induction, you can easily see that the degree of kn over k0 is the product of degrees k I plus 1 over ki, where I varies from 0 to n minus 1. So as an exercise, you can easily see that if L over K is a prime number, then if M is a subfield of L, then L over K is equal to L over M times M over K. But this is a prime number. So at least one of these must be P, the other must be 1. So let us say this is 1. So if M over K is 1, that means M as a vector space over K is one-dimensional. But if M is one-dimensional, you already know that 1 is always a basis of M. If M is one-dimensional over K, this is M is equal to K. But if L over M is equal to P, so that's what it is. So this implies there does not exist any proper intermediate fields between A. So the moral of the story is, by just looking at the degree, we are able to learn something about the extension. So the degree is a number. By looking at a number, you can conclude that this extension cannot have any proper intermediate subfields. So this is how we are going to use these notions to understand the extensions. All right? Now, so let us move on to the next notion, next concept or notion. So algebraic and the transcendental elements. So in introducing this notion, I'm going to present to you a very particular notation, a very useful notation and very important one. So let as usual, let L over K be an extension, and A be a subset of L. All right, and so let us take the intersection of all fields, subfields M, where M is a subfield of L, which contains both K and A. So all the subfields of L containing both K and A, this is denoted by K of A. So note that this intersection is not empty, because L is a subfield of L, which contains both K and A. So L participates in this intersection, and therefore this intersection is not an empty one. So this intersection is contained in L. And then this field, this is a field because it is being the intersection of fields. Intersection of fields is always a field. This is very trivial. So it's the field generated by A over A. It's a very important notion. This will recur throughout the course. or the field generated by A over K. So this is a constructive definition, construction. So let us see a uh, descriptive description of this field. It is as follows. So you have A sitting inside L, and consider the set S consisting of all finite products of elements where alpha I belongs to either A or 1. Okay, so S consists of all these elements, and let V be the K vector space generated by S. What do I mean by that? By this, so I have, so let us take S1 alpha 1 S1 plus alpha K SK, where Si belongs to S and alpha I belongs to K. So what I'm doing is all finite K linear combination of S. Okay, so that is that, as you can easily check, is a vector space, because if you have alpha I Si plus beta I Ti, so this is also a finite expression where SITI belongs to capital S and alpha I beta I belongs to K. So this is also a finite one, and therefore it belongs to V. And if you have any alpha belonging to K, and if you multiply alpha by some vector alpha I Si, this can be written as alpha alpha I Si, and this is also belongs to K. So this entire thing also belongs to V. So you have a scalar multiplication, you have addition, and therefore this becomes a vector space. So this, the K vector space generated by S is all consisting of all the finite linear combinations of elements of S with coefficients in K. All right. Now K of A is the set of quotients R over R1 over R2, where R1, R2 belongs to V, and R2 is 1, 0. So this is division process. So this is addition process. This is multiplication process. So all these are part of definition of a field. So in order to construct a field, you need to define what a multiplication is, what addition is, what division is. Okay, so that's exactly what is being done here. So K of A is the descriptive notion of K of A is like this, consisting of quotient of elements of the vector space V, which is again a K generated by A S over S, where S consists of the finite products of elements of A or 1. Okay, and for example, we had already seen Q of square root of 2. So here S is square root of 2. And if you take all the finite linear combinations, here A is the square root of 2. So S would be all finite linear combinations of all products of, so you have 2, you have square root of 2, square root of 2, square root of 2, which is 2 root 2, which is 2, which is square root of 2, and similarly, and so on and so forth. You have infinitely many elements. You have also one also is there. And then V would be all finite linear combinations of or Q, which is we have alpha plus beta square root of 2 plus like this. And again, once you have 2, you have 2 root 2. Every possible element, every element in V can be written as alpha plus beta square root of 2, where alpha and beta belongs to Q. And the Q of square root of 2 would be alpha plus beta square root of 2 over gamma plus delta square root of 2, where these two are non-zero. not both gamma, delta, or 0. Okay. So which when you multiply on the top by gamma minus square root of delta or gamma plus square root of delta, you can easily see that every possible element can be written as alpha plus beta square root of 2 for some different alpha and for some different beta, where alpha beta belongs to Q. So this is the, so let me know if you have any questions in this notation, because this is extremely important. And when you have finitely many elements, alpha 1, alpha 2, up to alpha n, so instead of writing k of a, you simply write it as k of alpha 1, alpha 2, up to alpha n. So this is the field generated by alpha 1, alpha 2, up to alpha n over k. For example, and if in the case when a is a single element, you call k of a as a simple extension over q. For example, C over R is a simple extension because C can be generated as R of I. Or Q of square root of 2 over Q is a simple extension because, yeah, this is generated by square root of 2 over Q. Okay. Now, so let L over K be an extension and let alpha be an element of L. And consider the polynomial A0, A1x plus kn x to the power of n, which is belonging to k bracket x. Okay. Now, the evaluation of f, at alpha is given by f of alpha is equal to k naught plus k1 alpha plus kn alpha to the power of n. This is what is called the evaluation of alpha. For example, if you take x square minus 2 is a polynomial over q bracket x, and let us pick let us consider this extension. Let us pick root 3. Root 3 whole square minus 2 would be 3 minus 2, which is equal to 1. So this is the evaluation of this polynomial at root 3. Here my alpha is root 3. And similarly, if you take another polynomial, x square minus 2x plus 1 is equal to 0. And here my alpha would be, let's say, root 3. This is my polynomial of q bracket x. Let us say root 5. Root 5 whole square minus 2 root 5 plus 1, which is 5 plus 1 is 6. 6 minus 2 root 5 is the evaluation of this polynomial x square minus 2x plus 1 at this alpha. Okay. So now based on this evaluation, we are going to define. So alpha is said to be algebraic over k if there exists some non-zero polynomial f of x in k bracket x such that f of alpha is equal to 0. So as you can see, square root of 2 is an algebraic element of R over Q because square root of 2 satisfies this polynomial. And not only this polynomial, it satisfies this polynomial also. Because once you substitute, this becomes 0, it doesn't matter what this is. So this is also 0. So there are infinitely many polynomials which square root of 2 satisfies. So that means i.e. you can write it in this f is alpha is the root of some non-zero polynomial over k. So whenever a polynomial has coefficients in k, okay, so these are called the coefficients. So this is my indeterminate x. These are called the coefficients of the polynomial. So if the coefficients belong to a field, you say that the polynomial is defined over that field. So in this particular case, we say that this polynomial f of x is defined over k. Okay. So if alpha is a root of some non-zero polynomial, you say that alpha is algebraic over k. Okay. If alpha is not algebraic over k, then alpha is said to be transcendental over Q. So for example, if you consider the extension R over Q, and if you consider pi, which belongs to R, which belongs to E, so these are transcendental elements. The proof is extremely difficult. Yeah, but you can easily, Cantor's theory shows that a set of algebraic elements is countable, and then since R is countable, it follows set of transcendental elements is uncountable. Okay. Now, so let us express these notions in terms of mappings. Which is extremely useful. So let E denotes the evaluation, and alpha denotes the evaluation at the point alpha. You take a polynomial in K bracket X, and if you take a polynomial and alpha is an element of L, take a polynomial and then you send it to f of alpha. So f of alpha is an element of L. So if the kernel of E alpha is non-trivial, so 0 always belongs to the kernel of E alpha. But apart from 0, if there are some non-zero polynomials, you say alpha is algebraic, because that's precisely what it means to say kernel of E alpha is non-zero. If kernel of E alpha is 0, then you say alpha is transcendental. Okay. So what is the use of expressing these notions in terms of evaluation maps? Because we know a lot about this ring. K bracket X, you already know, is a PID. In a PID, you know that every non-zero ideal, non-zero prime ideal, is maximal. So every ideal is a principal ideal in a PID, but every non-zero prime ideal is also maximal ideal. In particular, you already know that kernel of any ring, if you have a ring homomorphism phi from R to S, kernel of phi is always a prime ideal, no matter what that phi is and what those R and S are. Assuming that R and S are non-zero rings, and assuming that phi of 1 is equal to 1. So this is a basic requirement for a ring homomorphism which we had adopted. So kernel of phi is always a prime ideal. So in particular, if kernel of E alpha is a prime ideal, and if kernel of E alpha is non-zero, so that alpha is algebraic, we know that it is a maximal ideal. Okay. On top of it, kernel of E alpha is generated by a single element, M sub alpha. Let us denote it by, because K bracket X is a PID. Okay. So K bracket X is a PID. So this M alpha can be taken to be monic. If M alpha is equal to, let us say, K naught plus K1 X plus Kn minus 1 x to the power of n minus 1 plus x to the power of c. So polynomial is said to be monic if the coefficient of the highest degree monomial is equal to 1. So this is the monomial. So monomials are of the form a x to the power of I. These are monomials, and this is called the coefficient. So okay. So the highest degree, this is called the degree of the monomial. So the coefficient of the highest degree monomial is 1. So such a polynomial is called monic. You can always ensure that because K is a field, you can always ensure that the polynomial which generates any ideal is always monic. Now, you know that M alpha is prime, the kernel of E alpha is a prime ideal. And you know that prime ideal means it should be generated by an irreducible element. And also you know that it is a maximal ideal. So therefore, E alpha factors as, so by the first isomorphism theorem, this factors as this fact, E alpha tilde. And the image of this, so by first isomorphism theorem of, so if you know that phi from R to S is a ring homomorphism, and by the first isomorphism theorem, R mod kernel of phi is isomorphic to image of phi of rings. Right? You know this basic theorem in ring theory. The same notion, the same thing, because ring field is a particular type of ring, so we can apply the first isomorphism theorem, and let us call that map to be E alpha tilde, and the image of E alpha tilde is A of alpha. Okay, so we will show in the next class, and we'll continue from there.